by representation in English. And also, like, if you have any question, don't hesitate to ask. I don't mind like interrupting the presentation just to answer a question. And the topic of today's talk will be around multi-instance learning. So it's a machine learning framework that allows you to learn from a bag of samples instead of a single example, which is more traditional. So although I will be more focused in draw discovery, there are nice way to use the search framework in other fields like computational biology in general, and I will give specific example on how that could fit different kind of task in computational chemistry or computational biology. And maybe before talking about the science itself, I will take a few seconds to talk about what we are building at Valence. And so at Valence Discovery, we are building tooling that to support drug discovery like from start to finish. So our mission is really to build AI system to empower drug discovery scientists in order to unlock therapeutic options for previously untractable disease. And for that purpose, we are focusing on a lot of areas regarding drug discovery. So one that is quite obvious is the screening and scoring. So if you have a given chemical compound, you might want to know to try to predict its chemical property, but also know whether it can bind to a given protein target, or if it has any kind of like activity that might be relevant for the program that you're working on. And for that, obviously, there are several ways to look at screening when you're trying to use machine learning for that. Either you can go by using only a ligand-based perspective, where basically you're trying to learn scoring function from a data set that is coming from an assay that you have built. And the goal here is to use machine learning technique to try to learn to predict some specific molecular properties that are relevant for your drug discovery program. But you can also do it from a structural perspective. So this is the more classical way of trying to use computer science in anything related to screening and scoring for drug discovery. So a good example of that would be docking. So you have a set of compounds, and your goal is to try to use any molecular dynamics or just docking to try to see whether your compound can bind to a given target. But you can think from a perspective of machine learning that there might be a way for you to improve that the scoring function for docking, for example. I don't know if people are familiar with that, but there has been a lot of hybrid system that use both molecular dynamics and machine learning to try to better characterize protein ligand or protein complexes. So at Valence, we are looking at it from both perspectives. So we want on one side to build a better scoring function that can take into account the target of the structure of the target, sorry, in such a way, for example, where you have a given binding pocket and you want to know whether you can design compound that will fit inside that binding pocket, or whether you can accurately predict if a compound can bind inside that pocket. But we're also using a lot of ligand-based approach, where you just have a data set of compound with measured property, and you try to build a predator that will be used to predict the property of a new compound. And there are a lot of challenges around that, and the most obvious one is the fact that when you are working in the drug discovery field, usually there's not a lot of data, so the data sets are quite sparse and really small. And for people that are familiar with deep learning, this is in complete contrast with the requirement of data that you need for deploying. So we are talking about like 1,000 of data sample for things like computer vision, but in a drug discovery program, you might have only like 8 dozen compound, and you want to like to learn something from that. So there's a lot of challenges around that. And the advance to make that possible is by taking advantage of things like few-shot learning out of the distribution generalization, and also the fact that we can build like better algorithm for molecular property prediction. Other thing that we are also doing, and that is required when we talk about AI for drug discovery, is around generative design. So here again, there are different ways of looking at it. So the goal here is to design new compounds that might have never been seen before, but that could have interesting property for a program that you're pursuing. So here again, you can see, you can try to design compound from a structure-based perspective. So the one key question here is that given the structure of the target that we are interested in, can we design compound that will bind to that by, for example, leveraging constraint that we have around the binding pocket? So the compound should be able to fit inside that binding pocket, but also to take advantage of the type of interaction that the compound could have inside that binding pocket. So things like will the compound be making some form of like a hydrogen bond bonding, or should it be making some hydrophobic interaction and so on? So leveraging the structure of the target to do that will be is something that is of interest. But you can also think of it from a purely ligand-based perspective, where that can be useful. For example, if you don't have any the structure of your target. So it happens a lot of time where you are pursuing a drug discovery program, but you don't have there's no crystal structure of the target, because you don't even know the mechanism of action of the therapy that you're trying to pursue. And in this case, it's more about using things like cellular assay, where you kind of like have a response of using a specific compound, how it reacts with its effect on a cellular system. And here you can still like use that kind of data set to build generative model that will help in suggesting new compounds that will have a key molecular property of interest for you. But another challenge around that is obviously it's not enough to have molecules that are active. You also need to take into account a secondary objective, like the fact that the molecule needs to be to have ease of synthesis. So if you design a molecule that you cannot make in a lab, it's kind of pointless. So you need to take these kind of things into account. But also the fact that your molecule needs to be stable, be non-toxic, have good permeability in general. And if you are working in things like brain, for example, you need to like have some property like CNS-like property for your molecule. And on top of all of those, there's also a PAR that corresponds to MPO, so multi-parameter optimization. So now that you know that you have a scaling function that works, that you are able to design a new chemical matter, can you use both of these together to optimize for a set of property? So it can be things like starting from a chemical series of interest for you, and you want to like to stay in that chemical space. So using your scaling function and your generative model, you can try to optimize on those variety of parameters while staying in that chemical space. But another thing that is quite that you encounter quite often is scaffold hopping. And so the idea here is that while we have a chemical series that we know have some nice property, but what we want to end up with is a completely new novel compound that does not share the same scaffold. And one reason why you want that will be around IP. So if someone has an IP on the scaffold, you might want to to suggest a completely different scaffold for that. And the last part of what we are doing is really around integration and collaboration. And so, like, you can have all the best machine learning algorithm that you want, but if people are not using that, or if it's not taking into account some kind of insight that people that have been working on a project for a long time have, it might not be that very helpful. So like finding a way to capture the insight of chemists or biologists that have been working on a project, and also developing infrastructure to allow easier collaboration between data scientists and life scientists is something that is of interest for us. So now that I can kind of give a quick overview of where AI can help in terms of drug discovery, let's go back to the key challenges that we have, which is how can we build accurate model for very localized chemistry. So I'm talking about like a data set that is not very diverse and most likely like only having a single scaffold, but it's very, very small too. So how can we use this state-of-the-art AI model in the case of drug discovery where we don't have a large data set? And by large data set, I mean a few thousand compounds, but also because we cannot have large data sets in drug discovery. Like if you look at the public database, for example, you can have like a few million compounds in PubChem or Campbell, but usually those data are not of interest, because the data that is of interest in a given project will be, for example, a data where you have an assay giving a target, and on that, which is the data that is relevant for your program, you only have at most a few hundred compounds that you are testing, because testing is expensive. So back to the question, so how can we adapt AI model to this kind of constraints? And there are several ways of doing that. One obviously is to have a better uncertainty calibration. So if you are able to build model that take into account the uncertainty of a prediction, that we can calibrate further in a framework like active learning. So you kind of run several cycle of design make test, and at each cycle you can take into account the uncertainty of the AI model prediction to further calibrate and improve the AI model for the next cycle. So that allows you to get quicker to the objective, to the goal of your program by only testing a few components at a time. Another way of doing that is to think of it from a method perspective. So we know right now that there's a lot of advance in anything related to feature learning. So for example, like how can we learn model from as few as like 2 or 5 example of data, and there are good example of that in computer vision, for example. And the other thing that is linked to feature learning is obviously out of our distribution generalization. So how can we build a model that has only seen a part of the distribution? So in our case, a small part of the chemical distribution, but be able to keep high model performance in another part of the chemical distribution that we have never seen. And this is important because most AI system or AI model are trained assuming RID, which just does not reflect like the reality of life in general or drug discovery. And the last thing, which is what I will be focusing today, is around representation. So instead of trying to like invest in better algorithm or trying to like build like complex protocol for improving the model, we can instead try to like just find a way to improve the molecular representation. So to give an example, if you're trying to build a predictive model using machine learning for drug discovery, for example, you need a way to represent molecule. and there are a lot of ways to do that. But you need to ensure that the molecular representation that you're using is capturing not only the complexity of chemistry, but it's also relevant to the task that you're trying to learn. And I will give some example in the next slide. Okay, so a question that you can ask yourself is, for machine learning applied to drug discovery in chemistry in general, what is a good molecular representation? And if you think about it, if you're trying to translate a molecule into something that an algorithm can learn from, there are a few things that you will need your representation to fulfill. So first, obviously, it will be around information preservation. So your representation should be faithful to the actual knowledge that you have around the chemistry. So if there is supposed to be like a bond between two atoms, the representation should capture that when you are trying to use it. But also accuracy and robustness. So by accuracy, I mean that it should be accurate enough compared to our understanding of the molecule. So a good example is if at a position of your molecule you have a carbon atom, your representation should be accurate in a sense that it knows that that atom is a carbon atom and not some other atom like oxygen. The other thing is robustness. So robustness in this case means that if I'm doing small changes to the molecular graph, I should maintain the extent of the change that I'm doing on the molecular graph should be reflected to the extent of the changes that I'm seeing in the representation. So if I add only one atom to a molecular graph in my representation between the two versions of the molecule, they should be quite close compared to if I add like a full molecular fragment. And aside from that, obviously, you also need to take into account the fact that the representation should be compatible with machine learning algorithm. So it's a bit pointless to have a very good representation, but you don't have any machine learning algorithm that can learn from that. And lastly, the representation also should be relevant to a task. And I can give an example for that. So let's say that your representation that you're using for your compound, just counting the number of carbon atoms that you have in your molecule. This kind of representation is it's not very useful when you are looking at like complex tasks like binding to a target. So building a molecular representation need to take all those things into account. Okay, so maybe a question that, given everything that you have seen so far, a question that you can ask yourself is, what are the molecular representations that we have right now? And there are a lot of them, and the most common one are handcrafted molecular representation. So there have been people that have designed some kind of feature that you can extract from a molecular graph. So it can be things like I was saying before, like counting the number of carbon in the molecule, but also maybe having a way to like to assess the C log P, which means lipophilicity of the molecule, and other things like that. But there are also molecular representation like fingerprint, where basically the goal here is to take the molecular graph and apply a hashing function on top of that, which will give us at the end a binary vector. But there are also a representation of molecules as a string of characters. So this is a common SMILE representation. You can also think of it from more molecular dynamic perspective, like having a electronic density or looking at the energy potential of your molecule. But what is more common right now is people representing the molecule as a molecular graph and using things like a graph neural network on top of that to do the prediction. So each of these molecular representation has its own strength and limitation. So for example, anything that is a handcraft, you might ask yourself that there's a lot that you might be missing because what kind of representation are fixed. So it's similar to people, for people that are familiar to what we are doing in deep learning before, for computer vision before CNN. So people where will look at the image and like design some kind of like feature that will be relevant for the task that you try to predict. But right now there's a shift in molecular representation where we are trying more and more to have a form of learn feature. So letting the model itself learn the relevant feature that it needs to use for its prediction. And this is where GNN in general are quite interesting. So we can just like take a molecular graph where bond and edges and nodes of the graph are labeled by the bonds and the atoms in the graph. And we can have some form of label on the edges and the nodes, which will correspond, for example, to the atom type or the bond type, and so on. And in this specific way of seeing molecule, there has been a lot of success. So there's a new field in machine learning that's called geometric deep learning, and GNN are part of that. And in general, when we are talking about geometric deep learning, the nice thing about that is you don't need to have handcraft feature because the graph neural network will learn all the relevant feature for the task that you're trying to predict. And how it works, there are different kind of like GNN and research passing neural network, but the easiest one, like one that is like easier to explain is this kind of like information aggregation. So you start from your graph where you have information on all the nodes, and every time that you are building a layer, you are doing message passing, you are getting information from your neighbor that you are aggregating to update your own information. And at the end of that system, you can do a pooling across all the node feature to get a representation of your graph. So this is quite nice, and it's quite similar to what people have for CNN, for example. And there has been a lot of promises around what geometric deep learning can bring to machine learning in general, but specifically to data that can be encoded as graph. And a good example for that would be to look at things like AlphaFold and so on, where we kind of see like what this kind of method can do. But this method also have a lot of limitations. So one of the most obvious one is overspouting, and the overspouting come from the fact that if you want to like to understand better the molecular graph, you need to update the node information from your neighbor several times. So like if don't know if you can see my cursor, maybe not. But if I want to like to get an information from a neighbor that is maybe 5 bonds away from me, I will need to do 5 message passing to get that. But the issue is that the higher is the number of message passing that I'm doing, the higher is the smoothing that I'm doing, because I'm kind of aggregating all the information together. That means that each node is not unique anymore in the term of information that is capturing. So at the end, all nodes will have like a kind of similar representation, and which is what we call like oversmoothing. And we also know that graph neural network in particular, it's hard to train them in very low data regions, so you need a lot of data to be able to use them properly. So there has been a lot of work in trying to like to offset some of these limitations. So I'm highlighting here some of the work that we did internally. So One of them was using a hierarchical clustering. So instead of doing a global pooling where we are aggregating all the node feature, what we can do is to do it in a hierarchical way where we are grouping together nodes that share some similar environment and doing the pooling in a hierarchical way. So it's, as you can see here, there are step in the pooling process, which is quite similar to what is done in CNN, for example. Other things will be around how we aggregate information for our neighbor, for a node. So we have proposed like a better way to aggregate that information that retain the maximum amount of information. There are also, especially for anything related to molecular graph, we know that molecules exist in the distribution of conformation, and in that distribution of conformation is the 3D aspect of a molecule that has an impact on this activity. So instead of trying to only focus on learning from the 2D graph, what if we bring more information from the 3D view of the molecule? And we have shown that by using that, we can kind of improve the performance in downstream stacks. Okay. So as I was talking about, GNN for drug discovery have had a lot of successes, but still we know some of their limitations. And one key limitation is that GNN are looking into a 2D graph, molecular graph. So there's a lot of information that is missing when you think about the conformation that the molecule can adopt. But when you think also about things like stereoisomerism, so if you have things like a chirality in your molecule, so how do you properly capture that in a graph neural network? It is challenging. There are ways for you to encode that information on the bond or atoms. But what we have seen people doing recently is to have a kind of model that learn from the molecular graph directly using something like a GNN, but also use some fixed descriptor representation of the molecule. So in that case, can be 2D or 3D descriptor or fingerprints. And the goal here is to have this kind of a parallel way of learning and then aggregating that information to predict the molecular property. And so the key hypothesis here is that there is information about the molecule that we might be missing when we are only looking at a 2D graph perspective, and especially when you're using a GNN. And this kind of information can be better captured by other kind of molecular representation. So what if we try to generalize that perspective not only to just GNN and FIS descriptor of molecule, but to any kind of molecular representation? And this is the purpose of this task. So if I go back to my hypothesis again, is we know that for a given molecule, we have a lot of ways to represent that molecule. And we also know that all those representations are not necessarily useful. So there are some that might do better than others when we are working on a given property that we want to predict. And so the key hypothesis here is that, well, obviously we can search over all the representation of the molecule. So think of it as like doing hyperparameter tuning. What we want to show, to demonstrate, and this is our key hypothesis, is that on all of these representation, there is one that is more relevant to the task and that preserves the most information with respect to the task. So there's what I'm saying by that is that one of these representations work better than the other for the task that you're trying to predict. So should we try to just search over all of these kind of molecular perspectives that you have? Or maybe is there a way where we can just learn from all of them together without overfitting? And that is where the concept of multi-instance comes into play. So with multi-instance learning, what we are trying to do is, in typical machine learning, you have a sample and you have a value associated to that sample that you want to predict. But in the case of multi-instance, what we have instead is we have a bag of sample, and we want to map that full set of example to a single value. So if you look at the illustration that you have at the left side, the task here is not to predict whether one of these dots inside are blue or red, but to predict whether the full bag of dots is positive. That means that there's at least one dot inside that is red, or is negative. That means that there's no red dot inside. And why would that be interesting? Because here, what you're basically doing is you can see a molecule as a bag, and all the dots inside are potential molecular representation. And in our task, what we are trying to produce is basically saying that in all these molecular representation that we have for that specific molecule, there is at least one representation that is predictive for our task. So obviously that involves the notion of finding a way to encode all of these representation in a way that is permutation invariant. And by that, what I mean is that if I take the bag of sample and I shake it, it shouldn't change the value that I'm trying to predict. It should be the same regardless. And why is multi-instance learning interesting is, well, if you think about it, we are already doing that in biology and chemistry already. So if you take a molecule that is active for a given target, we know that that molecule exists in a distribution of conformation, but also that not all of these conformations are active. There's only a selected subset of that distribution of conformation that is bioactive. So that means that like the molecule can adopt some conformation that might not bind to the target. And in case of docking or binding in general, it's really like the cost, the energy cost that matter for us. Like, is the molecule able to adopt that conformation that bind easily without a huge cost in entropy or not? And in what we're trying to do with like multi-instance learning applied to drug discovery is to kind of like generalize that idea. So let's take a step back, and instead of thinking about like molecular representation, let's think about molecular conformation. So for a given molecule, we have a distribution of conformation, and we know that not all of these conformation will bind to a target or will be active given some kind of measurement that we are looking at. But still, if there is some conformation that bind really strongly to a target, that means that that molecule is potentially active. And the goal here is to like maybe learn from all of this distribution of conformation, and find a way to aggregate the information that we can get from all of them to arrive at a conclusion to whether the molecule, given that distribution of conformation, is active for a target or not. So this is quite similar to some other idea that's called multi-view. And to give a good example of that, if I take, let's say that I want to like to understand some biomarkers for some disease, for example. And obviously, I might want to look at things like proteomics or transcriptomics or genomics in general. So maybe the marker for that disease will be something that comes from transcriptomics instead of looking at things that come from proteomics and so on. But maybe what I can just do is to have that multiple perspective way of thinking, and try to like leverage all the omics data that I have to predict whether they are kind of like indicative of the disease or not. So those kind of two concepts are quite familiar, and depending on who you're talking to, they're kind of the same, or people also kind of think that they are like different enough to be considered as separate concepts. So here, one of the things that we are looking at is obviously finding a way to aggregate the information of all the examples that I have in my bag. And as I was saying before, we need to find a way that is find an aggregation that is permutation invariant. So it doesn't matter the order that I have in my list of like representation. I should have the same kind of output at the end. And a good way to like to assess whether a function is a permutation invariant is this equation here, but we kind of like explain it in detail with some example. But before that, let's look at how we can learn in a multi-instance framework. So assume that I have a molecule, and then on that molecule I have different way of representing it. So I have different representation for one single molecule. And what I want is a single value at the end of my learning process that will tell me whether the molecule is active for a given target or not. Well, there are two paradigms for learning in that framework. So the first one is I can just try to learn a different model on each of these representations, and each of these models will give me a single output that corresponds to a task that I want to predict. And my goal here is to then use a function that will aggregate all of these prediction into a single value that corresponds to the value of the set of representation. So this is quite familiar to what we do when we're talking about ensemble learning. So you kind of learn like different model on different kind of like part of data set, and to get confidence on the prediction that you're making, you aggregate them by taking, for example, the mean to get your output. The difference here is that the representation that we have from our input are different from one model to the other. The other way of looking at it is maybe instead of trying to predict a single value for each of the model, what I can do is to kind of derive a new representation for each of these single molecular representation that I have initially. And that new representation will be learned given the task that I have. And I can then aggregate that representation across all of the input that I have in my bag to then feed to a learning algorithm that will predict the value, the output value. So the difference here is that in one case, we are predicting the output value and then doing the aggregation. In the other case, we are predicting some intermediate feature representation. So we are doing a representation learning and then aggregating all the feature to get to a single value after by plugging on top of that a new learning algorithm that can be just be MLP, for example. So in this second case, we are learning a better molecular embedding that take advantage of all the variety that we have in molecular representation. Okay, so how can we actually do the aggregation? I was talking earlier about like just taking the mean of a prediction of the mean of the feature. So you can do that. And the mean, in fact, is we are aggregating the feature, but by giving to each of these sample that we want to aggregate, we give them a specific weight that is learned by the model itself. And that can be helpful because not only we will get an aggregated representation, but we also have the weight, the coefficient that is applied to each of these prediction or feature. And this is helpful because it also gives us an idea of interpretability, because if the weight on one given prediction or one given embedding that is learned is high, that means that the model is putting more focus on that, and that either means that that specific representation is relevant for our task, or is like is contributing a lot to a prediction that is being made. Okay, so given that I have presented that framework, is it actually like useful? Like if we implement that, and if you use it to like to run it on some benchmark, like do you get better results? And obviously, like when you look at the that multi-instance framework, you can quickly see that well, you are introducing more parameters to learn. You are introducing like like more dimension in terms of representation, but we still have the same issue that we have in drug discovery, which means that we don't have more samples. But it actually turns out that like if you you use that kind of like framework to and run it on one of the popular benchmark in machine learning for chemistry, which is TDC, you get results that are better than the TDC baseline. They have a leaderboard with the best kind of score of a model that have been trained by various kind of people, and you get good results despite the fact that we are still not dealing with the curse of the dimension here. But one thing that is a bit more interesting is that I was saying earlier that the type of aggregation that you use might matter a bit because depending on the aggregation that you're using, if you're using an attention-based mechanism, for example, you will get some form of interpretability. And that means also that you have additional parameters that you should try to tune when you're doing search for a best model. And if we run it and try to like to find out which one is the best kind of aggregation function to use, and if whether it changed based on the fact that we are doing an aggregation at the feature or instance level, we can easily like find out that it does matter a lot which kind of aggregation that you're using. And it also does matter a lot for some tasks, whether you are doing the aggregation at the feature level or if you're doing it at the instance level. But one thing that is quite consistent is that usually attention-based pooling, so aggregation tends to kind of score a bit higher. But also when you are using like a feature-based aggregation, so instead of like predicting the value and aggregating, you are predicting and embedding and learning on top of that. In some cases, it works a bit better. And this is also quite interesting because if you think about it, if you are predicting and embedding that you then aggregate after, you can leverage a variety of external data set to pre-train model that you can then transfer on a new task. So in that setting, multi-instance learning with some form of like attention mechanism for aggregation, with aggregation being done on the features instead of the instance, is useful for transfer learning. And the question that you can ask yourself is that, well, if we do that, we try to like to train on a large data set, in this case PCBA, that has like 400,000 molecules. We have more than that now, and a lot of tasks. And then we try to like to extract the new representation that we have learned and use that new representation to transfer to a new task. Do we perform better? And the answer is that it depends. So sometimes it's slightly better, sometimes it's just worse. So there's still like maybe a lot of things to investigate around like transfer from a larger data set that you have learned on. So a few way of like looking into that is maybe the tasks that you are learning on initially, you need to carefully pick them, but also you need to carefully pick or at least like have a variety of molecular representation that capture the most about the task itself. So it come back to what I was saying about your representation needs to be rich in information and be relevant to a task. So those are kind of like a condition that you still need to meet, regardless of the fact that you're doing transfer learning or not. Okay, so I think this is the last slide. So yes, multi-instance framework, it has a very interesting application for in machine learning for drug discovery. And at the same time, it also does have an interesting application for any kind of other orthogonal fields like computational biology and computational chemistry. If you go back to the example that I was giving about maybe trying to learn from all the omics data for your prediction, you can see that like there's a lot of like interesting application that you can have. And from the kind of result that we have so far, we can see that it's very competitive, especially if you're able to properly take advantage of pre-training and then transfer learning. It can be helpful. And I was saying before, if you're doing the aggregation using attention rates, you can get an idea of interpretability, and that will be helpful, for example, to select like a molecular representation if you want to like get out of that multi-instance framework. I understand that it's a very expensive way to do feature selection, but it does work, and as highlighted by the plot on the right side, where I'm showing the attention weight, so the score, the contribution of each of the different molecular representation that has been considered during the task prediction. So you can see that some of them are not contributing that much, and if you went like not giving you an idea of like whether they were relevant for that given task or not. So I think like there's still a lot of things that you can do with that type of framework, and it will be very interesting to like to see what people can come up with within that framework in general, or for multi-instance for anything related to machine learning for a life science field. I think I have some questions.
Yes, thank you so much, Emmanuel, for your presentation. It was very, very interesting. Yes, there is a question from Kay. He said, is there an example of a drug molecule which has been developed using one of this approach?
There are actually a lot. But what I can tell you is that there are a lot of like drugs that are in clinical trial right now. And a good example of AI-based drug that exists would be some of the work that have been done by in silicometin or some other kind of competitors that have been in the field for a long time. Same for like recreation therapeutics. So like it's not that they use these specific methods, but they use like any kind of machine learning model that they kind of to try to leverage for to accelerate or make the drug discovery process more efficient.
I have a question. On the page 6, you show layers. Not sure to understand, but I'm just wondering if the layers means the... yeah. So the layers for each node, it's represent an atom.
Are you talking about the left side or the right side?
The left side.
Okay. So on the left side is a classical message passing algorithm for the Grafton network, and the idea is that at each layer you aggregate information from your neighbor. So like if we start at the, can you see the red red dot, red
Yes.
node here? Yeah. So the red node, if you look at the graph that is at the left side, you can see that all its kind of neighbor are green nodes. So you are getting information from the green node at the first layer of message passing. But then these green nodes are also getting information from the neighborhoods. So that means that like at the second layer of message passing, you are getting information from the green node that are also getting information from their neighborhood. And then you are kind of like accumulate that with the more layer that you have during the message passing.
Okay, so the red is the ligand between all the molecules?
No, in that case, the red is just a node in your molecular graph, so it's an atom. And this process is only highlighting like the message passing algorithm. So which kind of information are you getting from each layer that you're applying during the GNN. So it's
Okay.
still not, it's only giving you the information that you have at the hand of applying 3 layer to the red node.
I see. In the case that we have many molecules, is that represented in one multiple layers, or it's separate graphs?
Yeah, so that's come down to what I was saying before about like doing aggregation for GNNs. So maybe this is a good example. So if you look at the first kind of first plot here, when you're doing message passing, you are updating the information of each node by itself independently, and that's what you are getting from this here. So when you are aggregating that information, you still have a molecular graph. So you still have like a graph with information at each node that you have updated. But if you want to get the representation of a full graph, you need to aggregate all those information that you have at the nodes. And you get that by performing a pooling mechanism on top of all the nodes. And that will give you like a single vector that corresponds to the representation of your molecular graph. So if you have like a set of molecules, for example, you will do that for all of the set of molecules and all of the molecules in the set, and you get like as many vectors that represent each of the molecules in the set.
I see. My second question is about the hierarchical clustering. You said that you use that. Did you use another type of clustering, or it just because the hierarchical clustering was the best for your case?
So in this case, it's not really hierarchical clustering as we use them in bioinformatics, for example. In this case, you kind of learn to map each node to a set. So like see it as it's not it's a learn algorithm. So you're not applying clustering, but instead you're trying to like to learn a weight of each node belonging to a set. So you compute. So like if you look at here at the second, the hierarchical clustering, where you have 2 nodes here, what you're doing during the learning process is to look at all the atoms in the graph and ask yourself uh, which of these nodes is it more likely to map to. So you learn that this kind of coefficient between the node in the graph and the new node of the smaller graph that correspond to the clustering of on top of the graph. And by having this kind of coefficient, then you can use that to map the nodes to the more likely set that it should belong to get more sparsity in the aggregation that you're doing. And then you do that several times to get to a single node that will give you the representation of your graph. So in contrast to the other one where you map all the node representation into a single vector, here you do it hierarchically, where you kind of like reduce your graph at each step, because by doing that you increase the chance of exchanging information between nodes that are far away in your graph.
I see. Oh yeah. About the I don't have the number of the page, but about the bags, there's bags with the blue and yes. So how do you define the molecules which is labeled like O or +1, negative or plus? Is it because of the physical, chemical properties of the molecule, or it just random? You put random molecules on the bag.
Yeah, so here, like each bag corresponds to a molecule actually, and the
Yes.
dots that you have inside the bags correspond to the molecular representation. So it's easier to grasp the concept when you are thinking of it with molecular conformation. So think of each bag as a molecule, a 2D molecular graph, and what you have inside the dots are all the 3D conformation that you can have with your molecule, because you can rotate on the bonds and everything. And the idea here is that when you're building your assay and you are testing a given molecule in the lab, for example, to see the biological response that you are getting out of it. So does it bind to a target and measure that? Or if you have a functional assay, like does it inhibit some like a target and so on. So you have a value that corresponds to that, and that value can be a discrete value, so any yes or not answer.
I see, I see.
And the bag here, your goal is to try to predict whether that bag, which is the molecule, has the yes or no answer. And you can think of it like in all the 3D distribution, 3D conformation that the molecule can adapt, maybe there's at least one that corresponds to a yes answer. And that means that that molecule as a whole should be a yes instead of a no. It's an hypothesis that is not true all the time, but it's a strong hypothesis for testing some idea around multi-instance learning.
I understand. Like for example, if you have some molecules that are inhibiting other molecules, so it's like 0, and for the one which is not, it's 1, and you put it on the back.
Yeah.
And then you learn the model. Oh, good. Oh yeah, for the page 13 is my last question. About the features importance, because it was cut, the YouTube videos was cut, and I was not listening out what you said. But did you use other means, max, and other metrics?
So if I go back here, so at one point we need to aggregate either the embeddings that you are learning or the output of the model, and some way of doing that are using these functions that are supposed to be invariant to permutation. And obviously using any of them is fine by itself. Some have like a property that others do not have. But in that case, what I was like suggesting is that maybe it makes sense to use some form of attention mechanism. So it will be the gated attention or the additive attention, because not only do you get an aggregation of the hands, but because attention mechanisms use some weight between all the things that you want to aggregate and the value itself. So you have an idea about which of the dot in the bag, for example, is contributing the most to the prediction that you're doing. So it gives you an idea of interpretability, which other methods are not getting you.
Nice. Perfect. Thank you so much, Emmanuel, for your presentation. So for now, we're going to start the networking session. I posted on the comments the link of Wonder application that we're going to use for the networking. So you can talk with Dr. Noutahi and other members, bioinformatician in Montreal. So thank you so much, and see you just right now. Thank you.
Thank you, Yasmin, for the invitation.
Thanks.